Hello, my name is Yannick Maust from TU Graz, and I will talk about efficient congest algorithms for the Lovász local lemma. This is joint work with Yara Ito from Aalto University. So before we dive into the details of the success story of distributed algorithms and the Lovász local lemma, let's look at the definition of the lemma. So an LLL instance is given by a set of bad events, and these are events that you want to avoid, and the events are defined over some discrete set of random variables. Additionally, you know that there's an upper bound on the probability for each bad event to happen. There's a common upper bound P. And then there's another parameter associated with this setting, the dependency degree. That's a maximum number of events that one single event can depend on. And now the famous LLL lemma states that if the standard LLL criterion, I don't have to look at the criterion right now, is satisfied, then there exists an assignment to the variables which avoids all bad events. The success of this lemma really came when the first constructed versions appeared. Algorithms which you can use to actually compute an assignment of these variables. In the distributed setting, we often don't work with the standard LLL criterion, but with stronger criteria. So for example, with the polynomial LLL criterion, which just means that the relationship between the upper bound P on the probability that the bad event happens and the dependency degree is better in the sense that it has a smaller probability, or even an exponential LLL criterion where the probability is even smaller. When we study the LLL problem in the distributed setting, we need to consider the so-called dependency graph. In this graph, each event has one vertex, and there's an edge between two events if they share a variable. And of course, a variable can be shared by multiple events, which then form a clique. And now, in the distributed setting, we consider the standard local and congest model over this dependency graph. That is, each of these bad event nodes is a computer. While this sounds a bit awkward, in all applications, one quickly realizes that this definition actually makes sense. So on this dependency graph, now the nodes can perform the local and congest algorithms that we know. So they can do synchronous message parsing in discrete synchronous rounds through the edges of this graph. And the overall goal is to compute an assignment of the variables such that no bad event occurs. And the time complexity is always just the number of synchronous rounds until each node has produced its output. So produced the values for the variables that it holds. And there are two main models that I mentioned. The local model, here the message size is unbounded, and the congest model, in which a node can only send order of log n bits in one message. And here you already realize that the LLL in this general setting doesn't make sense, because in the congest model, you should at least be able to send the value of a variable to your neighbor. And if your event depends on the value of a variable which is held by your immediate neighbor, you should also be able to learn this. And you should actually learn all the values of the variables that are needed to determine the status of your event. And for that purpose, we define so-called range-bounded LLLs. So what we do here is we bound by poly D, D is the dependency degree, so also the degree in this graph, the range of any variable, and also the number of variables per node. Note that this range-bounded LLL still has this local flavor of LLL. You can see the LLL lemma, the Lovász local lemma, as a local variant of a standard union bound, and we maintain this local behavior here in the range bounded setting. So there's a lot of previous work in a distributed setting on the Lovász local lemma, primarily in the local model. So for example, the log squared n algorithm by Moser and Tardos, or a log n algorithm by Chung, Pitti, and Su. Both of these algorithms also work in the CONGEST model if restricted to range-bounded LLL instances. When there's a lower bound randomized of log n rounds and deterministic of log n rounds, the conjecture on that this randomized lower bound is tight on bounded degree graphs, and an algorithm which at least in the local model and on bounded degree graphs reaches polylog log n rounds, which was a big breakthrough. Interestingly, if you go to special graph classes to trees, this lower bound is tight and one can obtain a log n round algorithm in the local model. And if you consider the very special setting of LLL instances with an exponential LLL criterion, then one can even go below this lower bound and get a log star n algorithm deterministically. LLL is so central to the area because it can be applied in very diverse ways. So for example, it can be used to solve individual problems such as Sinclair's orientation problem or defective coloring variants. But often it's not clear how to actually use LLL, and it's not immediate how to come up with an LLL process for the individual problem that you want to solve. And this is why it's also not immediate to see the most important application in my point of view, which is in the LCL theory. So this is the state of the art for LCLs on trees in the local model. So this is the complexity landscape, meaning what you see here are different asymptotic complexities. And when there is an LCL problem with this complexity, for example, square root n, you have a bullet here. Whenever there's an x, you know that no problem has the complexity in this area. And these orange x's are either directly or indirectly only obtained due to LLL algorithms or LLL statements. Because what Chung, Kopelowitz, and Petty showed is that any algorithm which has a sublogarithmic time local algorithm, so which lies down here, can be solved through an LLL. And then on trees, the complexity of LLL, as we've seen before, is log n, which says any problem which is below log n can be solved in log n rounds. The other x's follow with different reductions. So here we can see the different papers which have shown all of these results. And it's actually true that on trees, the complexity landscape in the CONGEST model is exactly the same. And here also, the LLL problem, at least indirectly, played an important role. In our paper, we study more LCLs on general graphs and the LLL problem on general graphs, not on trees. And this is the state of the art for LCLs on general graphs. Again, in the local model. Here, the green areas are dense areas, meaning there exists an LCL problem for each of the, for a dense subset of complexities in these areas. We do have the same gap from sublogarithmic to the complexity of an LLL algorithm. But here on general graphs in the local model, the complexity of the LLL problem is not known to be log n. We have the log n lower bound, but the best upper bound is only polylog n. So there's a polynomial gap in between here. And what we show in this paper is that we can also get the same asymptotic runtime in the CONGEST model for the LLL. And this is why our LLL result also has implications on the LCL theory on general bounded degree graphs. LCLs are always defined on bounded degree graphs. And this is in particular interesting because now, if you look at the state of the art or what we know here in the sublogarithmic regime, it looks very similar for both models. But we cannot claim that it's exactly the same because there are parts which we don't know. But what we know is, and actually, that if you have a problem which is here sublogarithmic in here, it will also be sublogarithmic in this part. So the set of problems that fall into these green areas here are actually the same, and it at least seems to be that these areas are the same. And this is in stark contrast to the regime on general graphs above log n complexities, where this other paper up here shows that there is a problem which in the local model has a log n complexity, and in the CONGEST model, a much higher complexity of roughly square root n. So now that I've told you about our implications on the theory of LCLs, we can come to our main result, our polylog log n round randomized CONGEST algorithm for range-bounded Lovász local lemma on constant degree graphs with the polynomial LLL criterion. So on the next few slides, I will explain you how do we obtain this algorithm and what are the main ingredients to our algorithm. On a very, very high level idea, we use the shattering framework for LLL, which is a standard framework by Fisher and Ghaffari, and then which shatters the graph into small unsolved components. And then we use a bandwidth efficient, so CONGEST tailored derandomization method on the small components. So let's look into the details of this. So this Fisher-Ghaffari shattering framework works as follows. It consists of two phases, and in the first phase, the pre-shattering phase, we gradually set some of the variables with a certain backoff procedure, but the procedure is such that, at the end, we remove all the events which have all variables set, and we only remove events which are not, which do not hold. So basically, all these bad events here that we remove are avoided. And the bottom line here is that after we execute this pre-shattering phase here, which only takes constant time, because it on bounded degree graphs, because its runtime is mainly a poly-delta time, the remaining components only have order of log n size. No one would, like in the post-shattering phase, solve these remaining small components. And what one would like to do, but which doesn't work, is just use one of the standard, for example, Mozart-Taldus randomized algorithms for LLL on these small components, with the hope that instead of normally Mozart-Taldus runs in log squared n time, that it then runs in log n squared time. But the problem with doing this is that actually, if you run this Mozart-Taldus for this short amount of time, that also your failure probability is only with high probability in the size of the small components. So it's only going to be 1 over capital N, which is way too much as a failure probability compared to what you want to have. This is why we here, and this is usually what's done in the shattering framework, want to apply a deterministic algorithm for the small components. So let's look at this. We need a deterministic algorithm, but there's no single deterministic CONGEST algorithm known. And I don't know what the chances are for a deterministic CONGEST algorithm. In particular, like our final runtime goal here is polylog log n rounds, which is pretty fast. It's like also the state of the art in the local model here. But on the positive side, what we have is that the components are small. And now what will be crucial for us is that in comparison to the original graph, the bandwidth is small, it's only log n. But in comparison to the component size, our bandwidth is actually not too small. It's going to be in the order of the component size, which is actually pretty good. So with these parts on the positive side, what we do is we devise a de-randomization algorithm. So I will now in the next slides first show you how do we get the de-randomization, which runs in diameter times polylog log n rounds. But the diameter of such a small component can be very large. So then in the second step, I'll show you how do we reduce the diameter. So this is our approach to obtain a de-randomization deterministic algorithm in diameter time. So in each component, we just elect a leader. And now the leader can collect the whole topology of the component. Afterwards, it uses a method of conditional probabilities to find good random bits for each of the nodes, such that when afterwards, with these good random bits, when they execute the randomized algorithm, I haven't told you which one, the LLL is solved. So why does this work here? For the first step, well, why can we collect in a CONGEST model the whole topology of the component at a leader? Because generally you cannot learn the whole topology of a graph efficiently in the CONGEST model. But here we can, because the whole component, its topology, can be encoded with order of log n bits. And this is what we do. Why can we find good random bits? I won't go into the details of the method of conditional probabilities. For these, please go and read the paper. But I want to tell you that the essential part here is that we use the simple LLL algorithm that we de-randomize here by Chung, Petty, and Su, and it only uses very little randomness per node. Basically, it just uses poly log n bits of randomness per node on these small components. So actually the leader can here really determine good random bits for all of them and distribute them to all of the nodes of the component. So if we look at the runtime of this procedure, we basically notice two components. One is involved with the amount of data that we need to aggregate and distribute to the nodes. And here we see that due to the bandwidth, which is large in comparison with the size of the component, here we're already doing quite well. We have a polylog log n runtime. The second term, and this is where we're not doing well, is the diameter of the component, because this can be quite large. It can be the number of nodes, it can be the full log n. And the standard method in the local model to reduce the diameter for many problems, so for example, if you want to solve a coloring problem or the maximal independent set problem, it's a network decomposition. So network decomposition is a partition of the vertices into clusters of small diameter. And these are grouped into collections such that afterwards you can iterate through the collections and first process all green clusters, then all blue clusters, and then all gray clusters. It's a very standard tool in the local model. First of all, because in the local model, the small diameter immediately helps. But in the CONGEST model, it's much more difficult to exploit small diameter. But we've already seen on the previous slide that we can have an efficient algorithm if our diameter is small. But there are more problems in the CONGEST model that we'll talk about on the next few slides. And now we want to use this network decomposition on the small components and use it to get the diameter in our de-randomization method down. So instead of having one king for the whole small component, we compute such a network decomposition and have lots of these clusters. And then first we process all the green clusters. And we now want to, on all of these green clusters, de-randomize our algorithm at the same time. But what you realize, if you fix the random bits inside one of these clusters, you're going to influence parts outside of your cluster. Because in a T-round randomized algorithm that you want to de-randomize here, also nodes in distance up to T will read your random bits. So if you choose random bits in your cluster, it will have influence outside of you. So our first requirement here to actually use these network decompositions here is that the distance between clusters of the same color are at least of distance 2T if we want to de-randomize a T-round algorithm here. And this is already something which is not as easy in the CONGEST model. While you can simply compute a network decomposition of G to the 2T in the local model, this is more difficult in the CONGEST model. The second requirement that we need here is a so-called ID space independence. We want to run these algorithms efficiently on the small components. And by efficiently, we basically want to take the runtime on general graphs and replace the number of nodes in this runtime by the number of nodes in the small components. But very often, algorithms on general graphs are only efficient because they use that the ID space and the number of nodes only have a polynomial difference. So saying if you have n nodes, your ID space can only be polynomial in n. But here, if we run this algorithm on the small components, we have small components which have only size log n, but our ID space is still the very original ID space. So it's exponential in the component size. Of course, there are other things that I didn't tell you now, that you also have to deal with difficulties at the de-randomization. And when you fix the random bits for your cluster, should not make the life difficult for the nodes and clusters which are going to be processed in the future. So these are also some parts you need to be dealt with. But for now, let's focus on the network decomposition. To go to the literature and just take one of the existing network decomposition algorithms, but unfortunately none of them fulfilled our requirements. So for example, the first one here by Elkin and Nyman, it's a randomized algorithm. We cannot use it on the small components. Then the one by Ghaffari and Kuhn and Ghaffari and Portman, both of these, well, they have these properties, no ID space dependence, and they can be run with a large distance, but actually their runtime is really bad. They have this 2 to the square root log n runtime here, which is kind of outdated since the breakthrough result by Rosen and Ghaffari a few years ago. And it turned out that all the follow-up works either didn't work in CONGEST or were only satisfying our needs in one of the two parts here. So as a small side result in our work, we also devised a network decomposition algorithm, which is good with respect to all these parameters, meaning we get small diameter, we have a small polylog n runtime, and we get a small ID space dependence, and you can ensure the cluster distance that you want. Let me end with some open problems, and the most prominent one is for sure the complexity of the LLL problem. Can we get down to the lower bound of log n rounds? Can we actually prove that the Chang-Petty conjecture is true? It states that there exists a log n randomized algorithm for the Lovász local lemma in the local model for bounded Euclid graphs. And if it is true, we can also ask whether we can meet the same runtime in the CONGEST model, or can we not? But there are more questions related to LLL. So for example, LLL for now, constant delta, and I'm sure that LLL can do much more.